new chemistry. So there are several reactions I want to talk about today, but the most important of those is the Outlaw condensation, so I'm going to start there. The al comes from aldehyde, all comes from alcohol. And that reflects the fact that the product, the initial product, often has both an aldehyde and an alcohol. We're going to use the simplest example. We're going to use ethanol or acetaldehyde. And the important thing to know about the Outlaw condensation is it is enolate chemistry. Generally base catalyzed. There are examples of acid catalyzed alcohols, but usually it's base catalyzed, and so you're working through enolate ions. So it only works if there's a hydrogen on the alpha carbon, because if there's no hydrogen on the alpha carbon, there's no what we call an enolizable proton. And the reaction doesn't go. So the reaction is pretty simple. It's usually just a catalytic amount of sodium hydroxide, or it doesn't matter, you can actually use plenty of sodium hydroxide if you want to. And after 3 steps, you get that thing which we call the aldol. Where there's the new carbon-carbon bond here. And you've got the alcohol, and you've got the aldehyde. Right? So that's where the name comes from. So we're making a bond from one alpha carbon of the donor to the carbonyl carbon of an acceptor. So if I want to break this up, right, this piece, that was the donor. And this piece over here, where the alcohol is the acceptor. The alcohols are not super stable, but the reaction can go further. To eliminate water. So we'll take the elements of water away. And make an alpha beta unsaturated carbonyl. In this case, an aldehyde. And those are super stable. This is now what we call a conjugated system. Conjugated simply means adjacent. So we have a carbon-carbon double bond and a carbon-oxygen double bond adjacent to one another, and that imparts special stability because now we have a phi system that overlaps over 4 atoms. The more atoms your pi electrons can be localized over, the better. Because you remember that electron's goal, every electron's goal in life is to simultaneously occupy all space. So the more nuclei it can interact with, the better the attractive force and the happier those electrons are. So this reaction is often driven forward by the stability of that compound. From an entropy standpoint, right, the formation of the alcohol is not very good because you've taken two molecules and you've made one molecule out of them. But from an entropy standpoint, this elimination of water is good because now you've taken one molecule and you've created an alphabet unsaturated carbonyl and a molecule of water. So generally we heat it, but you don't have to. Sometimes that elimination of water will go anyway, even without heat. But often you can heat it, and if you heat it enough, the water evaporates, and that also helps drive that reaction forward. So the Aldol reaction is completely reversible under the right conditions. If you take an alpha-beta unsaturated carbonyl group and treat it with hydroxide and water and heat it up, sometimes you can make it go back the other way. So let's think about the mechanism. It's 3 steps. This is the nucleophilic acetylation part. That's how it kind of falls into the category that we're working with nucleophilic acyl additions. We make the enolate and then we attack and protonate. And then this is an elimination, but it is not an E2 elimination because hydroxide ion is not a good leader group. So hydroxide isn't going to be kicked out in a standard E2 pathway. So that's the reaction. Let's talk about the mechanism. And then we'll discuss when the aldol condensation is useful. In this case, I showed it the donor molecule and the acceptor molecule were both ethanol. Right? So it's a symmetrical system. So it's always useful when your donor and acceptor are the same. But if your donor and acceptor are different, it becomes problematic. Feel free to stop me since you're here if I start erasing something and you're not done with it. So the mechanism for the aldol condensation, which you'll have the chance to reproduce multiple times because it's part of the pre-lab for the aldol condensation lab, and there's probably going to be a quiz on it, although most likely not Tuesday, probably next Thursday, because Tuesday is going to be a reactions quiz. So the mechanism. To show the mechanism, we need to show all those hydrogen bonds, carbon-hydrogen bonds on the alpha carbon, because the first thing we're going to do is deprotonate for the enolate. And you'll notice that I'm going to be showing all of these steps as equilibrium. This is an entirely equilibrium controlled reaction that's driven in the forward direction by the particular stability of the bond. So we have an enolate ion, and we just made water. There might have been some water present anyway, but if there wasn't, we just made some. The second step is going to be a nucleophilic attack of that enolate ion on a carbon of the second molecule. So here's my donor, here's my acceptor. And we're going to make a new carbon-carbon bond. And you'll notice that one of the nice things about the aldol condensation is the two components, the donor and the acceptor, are similar size. So that makes it what we call a convergent synthesis, where you're building up a lot of complexity in one step. And so it's not like we're adding one carbon at a time. We're taking two fairly simple molecules and making a significantly more complicated molecule. That new CC bond between the donor alpha carbon and the carbonyl carbon of the acceptor. So now we're going to protonate this oxygen here using the water that we made in the first step. alkoxide. And that's the aldol. So the first three steps is enolate formation and then a nucleophilic acyl addition where we attack the carbonyl carbon with a negatively charged nucleophile and then protonate the oxygen. That's kind of a standard base catalyzed nucleophilic acyl addition. Negatively charged nucleophile attacks, alkoxide ion gets protonated. Right? There are a lot of reactions that do that. If there are still additional alpha hydrogens, then base can remove one of those to form a new enolate. If there are not additional alpha hydrogens, if this were completely substituted, so these were both methyl groups, for example, step 4 couldn't happen. And if step 4 can't happen because there's no additional enolizable hydrogen, then the aldol condensation tends to reverse, and we don't actually get product. So that additional alpha hydrogen is important for driving it to the more stable alpha beta unsaturated carbonyl. So we'll bring that product over here. Enolate ion. In the last step, we lose hydroxide, which we can't do in E2 elimination because it's not a very good leaving group, but we can certainly do it here. So you'll notice in that last step when hydroxide leaves, we regenerate our capture. Hydroxide ion being negatively charged and pretty basic is a terrible leaving group, but it can leave when you're in basic solution in the first place. So we have hydroxide here, and we make water, right? And then we have water, and we make the hydroxide by taking that proton off, we generate hydroxide ion that we're then going to use in the enolate ion formation, right, which will make water again, and then we lose the hydroxide. So we're constantly going back and forth from having hydroxide ion to having water in the negative. So 5 steps, it's fairly straightforward, right? Enolate formation, nucleophilic attack, protonation is an alkoxide, and then another enolate formation and a loss of hydroxide. The key is to do those last 2 steps stepwise. When you take this hydrogen off, it is much more reasonable for the electron pair to go towards this negatively charged oxygen and have a resonance stabilized anion than it is for it to go this way and kick out the hydroxide in a E2 concerted pathway. So it's not conserved. It's forming the enolate, and then the enolate breaks down with loss of hydroxide. And the reason it does is to put these 2 double bonds in conjugation. Now every step is in equilibrium. So if I have a lot of water present, it can go back the other way, and the aldol product is not particularly stable, but it's as far as you can go if you don't have that second enolizable hydrogen. So this reaction works better for aldehydes than it does for ketones. Because for ketones, right, you're going to have another group here and another group there. That's going to stabilize this carbonyl group and make that nucleophilic attack less stable. The other thing you'll know from ketones is because there's going to be more substitution, you'll also have more steric hindrance at the aldol stage. Right? Because this hydrogen wouldn't be hydrogen, this would be some other carbon, and you're going to get steric hindrance. So when is the aldol condensation useful? We we've just seen that it's useful if your donor and your acceptor aldehyde are the same. And then the logical question becomes, is it possible to have different donor and acceptor? And the answer is yes, under certain conditions. One of the conditions where you can have different donor and acceptor molecules is when one molecule has no enolizable hydrogen. And thus can't act as a donor. And the other is when it's intramolecular with one product that's way more stable than the other. Give you a ring size. So you might have a choice between forming a 4-membered ring, which is not very stable, or forming a 6-membered ring, which is significantly more stable. These are called a crossed Outlaw, or a mixed Outlaw. When you're doing this one, though, where one of the molecules has no enolizable hydrogen and can only act as the acceptor, the order of addition of reagents becomes important. Because if you don't control the order of addition properly, your donor molecule will donate to itself instead of donating to the acceptor. Any donor molecule can be an acceptor. Because you can have a carbon alpha to, or hydrogen alpha to a carbonyl group, you still have the carbonyl group. And all you have to do to be an acceptor is to have a carbon oxygen double bond. To be a donor, you have to have the carbon oxygen double bond, and you have to have the alpha hydrogen. So it's not possible for something to be only a donor and not an acceptor, but it is possible for things to act as only an acceptor and not be capable of being a donor. So let's take these examples in turn. Right? So we know the Outlaw condensation is useful if your donor and acceptor are the same. It can be useful if one molecule is only an acceptor and not a donor, and it can be useful intramolecularly. So let's look at an example where you have one molecule that can act as a donor only. A donor or an acceptor, and one molecule that can act as an acceptor only. So something that doesn't have an alpha hydrogen, and the example would be benzaldehyde, because now we have an aromatic ring here, but there's no alpha hydrogen. Although I suspect at some point when I give a quiz or exam on this, someone's going to put a hydrogen on that carbon. But that will be 5 bonds, and that's not allowed, so you should probably try to avoid that. We refer to that as Texas carbon, because everything's bigger in Texas, including the valence of carbon. So try to avoid Texas carbon. So that can only act as an acceptor. So what we're going to do is we're going to add base to our compound. And only one enolate can form because there's only one kind of alcohol. we got that enolate ion. And now we have our aldehyde. It can act as the acceptor, it's our donor. Our alpha hydrogen is our acceptor. With our large particle positive charge of carbon. This can come in. Use your tap. Notice that when I draw these products, I'm taking the acceptor and drawing it on the left and not the donor, because that becomes easier to make that carbon-carbon bond and not end up with kind of a weird molecule. It's always easiest when you're drawing a carbonyl compound like that. The carbonyl could be on the far right of the molecule, so it's CO double bond OH rather than AHC double bond O. Okay. So there's my nucleophilic attack. I can do the proton transfer. Outlaw product. And I've got my product, my aldol. Notice that because this aldehyde had a primary carbon next to it, a CH2 group next to it, I still have this second enolizable hydrogen here. Which means I still have the ability to drive the reaction the rest of the way forward. By forming the enolate. And then I'll be able to use hydroxide in the last step. Through. Down hydroxide. Make the final product. So the reaction is making the alpha beta effect. You'll notice that in both cases I wrote the E isomer. Because the E isomer is more stable, and because this is an equilibrium reaction, Dr. Herman. So the E isomer is always the dominant isomer in the Alveolar condensation. So here's the question. How do we get this donor to donate to that and not to itself? Because once I have this donor, it could choose to completely ignore the benzaldehyde and just react with itself. nothing to prevent it from doing that. And then you can protonate that alkoxide, and then you can form the enolate again, and after 3 more steps, you might predict that you would make the other possible alpha beta unsaturated carbonyl compound. So how do we know? How do we get the donor to understand that this is the acceptor we wanted to donate to and not itself? Because you can always do an aldol condensation on itself, right, to make a symmetrical product. Any donor can act as an acceptor. So we've got to get it to recognize that it shouldn't donate to itself, it should donate to this other molecule. In some cases, what you'll see is you'll see a carbonyl group that is a better acceptor. So if your donor molecule were a ketone, right, because you've got electron donating groups on both sides, that carbonyl group is more stable. And so the aldehyde is a better acceptor than the ketone. But in this particular example, both of our molecules are aldehydes. So how do we prevent the donor from reacting with itself? And that's where the order of addition comes into play. And it's somewhat similar in nature to alkylation of the enolate ion, where you want to make sure that once the enolate ion is formed, it's way more likely to run into this molecule or collide with it than it is to collide with itself. So to make this reaction stop, we add our acceptor and base in a flask, and then we slowly drip the donor in. So what does that accomplish? What that accomplishes is we've got our acceptor in here as a base. But that base isn't really reacting with the acceptor. It is, right? It's forming a hydrate. So you've got that normal equilibrium where you have the aldehyde hydrate forming, but there's no proton for it to take off. But you've got a lot of this. You've got a high concentration. So when you add your donor, and in this case, we don't usually run it with catalytic quantities of hydroxide. We usually have lots of hydroxide. So when you add your donor, right, you're adding it slowly, so it's in low concentration. It's pretty likely to run into space. And forms the enolate. Which in this case looks like this. And then what you want is you want this to be an environment where there's a lot of the desired acceptor molecule and very little of the molecule that you prefer it not to donate to. So you drip in a little bit of the donor, it crashes into a hydroxide ion and forms the enolate ion. And that enolate ion is then in the presence of the large concentration, because you've got the entire quantity of your acceptor molecule already in solution. It's way more likely to collide with this than it is to collide with the next molecule back that you just dripped in very slowly. And when you drip in that next molecule, it's way more likely to collide with this base because there's a ton of this base around. than it is to collide two late ions that does not watch out. So you control what reaction occurs by controlling the relative concentration of the two aldehydes. High concentration of your acceptor aldehyde and a low concentration of your donor aldehyde causes it to go the way you want. It would also work, though, if your donor molecule is a ketone. Because the ketone is not a very good acceptor relative to the aldehyde, both because of sterics and because the ketone has R groups that are stabilizing partial positive. So you've got electron donating groups on both sides. If you've got a ketone, that makes that less reactive. So if your donor is a ketone and your acceptor is an aldehyde, you don't have to part with this order of addition thing. You can just have them mixed in together. Right? Because it's a better acceptor. The aldehyde is a better acceptor. Questions so far? Obviously, if both your molecules can be both donors and acceptors, there are now 4 possibilities, right? Donating to itself, and then the 2 cross, and you're going to get a mixture of 4 products. I showed that in one of the pre-recorded videos, and it's a nightmare. It's just molecules all over everywhere. You need something that's either going to control the reaction by thermodynamics because one product is more stable than the other, so that equilibrium will eventually drive off to the most stable product. Or you need a difference in kinetics, where the nucleophilic to addition step is more favorable for one case than for the other. So there are 2 different things involved in the reaction where you have only a single acceptor molecule and then one donor that can also be an acceptor. One is if your donor is a ketone, right? Because the aldehyde is a better acceptor than the ketone, so you can cause it to only be the donor. And the other is if you control your order of addition such that you're dripping your donor molecule in slowly to a solution of the base with the acceptor. What about the intramolecular? It's possible for your donor and acceptor to be in the same molecule. And the molecules that we make would do that. And there's an example. These molecules are often available by ozonolysis. Cyclic aldehydes. So if I'm working backwards to where that came from, it could have come from a 5-membered ring. By treating that ring with ozone. Sulfide or zinc and acetic acid, and I'll form an aldehyde on this side and a ketone on that side. So these kind of molecules that have a donor and acceptor together are readily available from compounds that don't have any oxygen in them in the first place. So if we add sodium hydroxide to this, what could happen? What are the possible things that could form when you add sodium hydroxide to this? And the molecule is called 5-oxo hexanol. Because there's that carbonyl group, and that's an oxo group. So this is 5-oxo hexanol. What could happen when 5-oxohexanol is treated with sodium hydroxide. To help us think about that, I'm going to redraw the molecule. All the alpha hydrogens drawn in explicitly. So there are 3 different alpha carbons, one on each side of the ketone and one next to the aldehyde. If you were a base, is there any reason for you to favor one of those hydrogens over any of the other hydrogens? Because we could theoretically get this one off or enolate. Or we could take that one off before we enolate. There are 3 possible enolates. Let's call this case A, and this case B, and this case C. So this is the enolate that comes from removing H A, and this is the enolate that comes from removing H B, and this is the enolate that comes from removing H C. Is there any difference in stability between A, B, and C?
Yeah. I would say B is the most stable.
So B is more stable than
Both of those.
A, right? Because this is a more substituted double bond. This double bond is equally substituted, right? It's got.
Oh, because it has the oxygen. I see.
So B is maybe a little bit more stable than C, also because you don't have that extra CH3. Well, but this CH3 is kind of donating electrons to destabilize the ion a little bit. So there's not likely to be a huge difference in stability between B and C, but B and C are both likely to be more stable than A because you've got more substitution on your double bond. You've got an alkyl group on there instead of just a CH3. So what would happen if each of those molecules reacted? Intramolecularly, so that the enolate donated to the other carbon oxygen bond. So we can push this down and have that push over there like that, form a new CC bond between this alpha carbon and this carbonyl double plus. To make that. Got the plus on that carbonyl, alpha carbon there, and forming no ring. We can do the same here. Just donate in, go around, do that. Most effectively. delta plus carbon that used to be the carbonyl, the aldehyde, and the alpha carbon. Or we can do this. We've got our new CC bond there between what used to be the alpha carbon, carbon 1, and carbonyl carbon with phosphate. In all cases, you'll notice that the alkoxide group is beta. The initial aldol is beta hydroxy carbonyl. Not on the carbon that's directly attached to the carbonyl, it's on the next one over. So let's consider the possibility of protonating each of those and see what those products look like. So if we protonate this one on the left, which is A, make that out. If I protonate B, draw correctly. Make that out. What's coming out? Better drawing. And if we protonate C, and I make this alcohol. I think I drew those all correctly, right? Got an aldehyde hanging off, and then on this other carbon, it's got the OH group. It's got the ketone hanging off, and then it's got the OH group there.
Why in this one is there 5 bonds? The one farthest right, there are 5 bonds on that carbon. The top carbon in the ring, left one. The hydrogen shouldn't be there,
The
right?
hydrogen's not there. That's why this hydrogen's there. You'll notice how that hydrogen disappeared and didn't actually show up here.
Yes.
Because it
I
wasn't
did
there.
notice.
So, is there any reason to favor one of these products over the other?
Yeah, the rings, the 6-membered ring is more stable than the 4-membered ring.
And because this is equilibrium, the 2 4-membered rings will not form. So even though this is the less stable, it's the least stable anyway, because 2 of the 3 possible aldol products are 4-membered rings, it's not going to be very favorable. The other thing you'll notice is if you wanted to continue, by taking off the additional alpha hydrogen and forming there anything not to like about that?
Yeah. Wouldn't that just open the ring?
We've just put an sp2 hybridized carbon in a ring. So there's even more ring strain now than there was there. And if you wanted to eliminate, now you put a second sp2 carbon into the ring, sp2 carbon into the ring. It's really not going to want to do that. So the elimination step, which is what usually drives the alcohol condensation forward, can't even happen. So the only product that you're going to get is the six-membered ring because of the product stability. And you will get it in two steps. Form the enolate. And then eliminate hydroxide. Or the aldehyde unsaturated carbonyl compound, which you'll recognize was the starting material for one of the quiz questions. So the net reaction of the ozonolysis pathway followed by this intramolecular pathway is to convert a 5-membered ring into a 6-membered ring. So with the intramolecular aldehyde condensation, usually one product is favored over the other product because that product is more stable. And so the equilibrium keeps going and you get all possible products, but eventually you'll get the more stable product on if it's thermodynamically controlled. In the case of the crossed aldol, which is not intramolecular, it can be thermodynamically controlled or more likely kinetically controlled, where you have one collision that's either more likely or lower in energy because you've got that larger particle on the carbon. And I apologize, we didn't take a break. I should have taken a break before we review this molecular. So let's take a little bit of a break now. You can ask me questions. Take a few minutes. I kind of wanted to make sure we got the whole aldol done.